So the specific theorem of Dirichlet is that K and L be relatively prime. K is the modulus. And there are infinitely many primes. Congruent to L mod K. Of course, this is of interest only when it's valid alpha. Of interest only when K is greater than 3, greater than 2. So this is Dirichlet's theorem. Many consider this theorem, proved in 1937, to be the starting point of analytic number theory. Riemann was influenced by Dirichlet. 1837. So many consider this to be the starting point of analytic number theory. So Dirichlet is often referred to as the father of analytic number theory. And Riemann definitely was influenced by Dirichlet. Although it was with Riemann's work that the full power of analysis was applied. But here you will see already some analytic tools coming in. So to begin with, just to get an idea of why something like this is quite a bit non-trivial to prove, let's just simply go back for a moment to Euclid's proof and see what the key idea is. Okay, so key idea in Euclid's proof. And we can adapt Euclid's proof to prove primes in certain arithmetic progressions. And then we need some tricks to get to certain other arithmetic progressions. But soon we run out of tricks because the number of moduli is infinite and consequently the number of arithmetic progressions is infinite. Okay, so the key idea in Euclid's proof is assume list of primes is finite. So P1, P2, PR is complete list. Then consider the number n, which is the product of these primes, and add 1 to it. Then the whole idea of Euclid's proof is there exists P that divides n, obviously, and P is automatically relatively prime to this product. Hence P is a new prime. So list is not complete. So whatever list you start with is always incomplete, and hence you have infinitely primes. So this is the idea of Euclid. Now this can be adapted in other situations. So for example, you can prove there are infinitely, so idea can be used. So Euclid's idea can be used to show theorem. There are infinitely many primes congruent to 3 mod 4. So what is so special about 4 and the residue class 3 mod 4? Well, what is special about 4 is there are really 2 classes of primes mod 4, 1 mod 4 and 3 mod 4. But between the 2, it's easier to confirm there are infinitely many primes in 3 mod 4. Why? So the proof goes, following Euclid, the proof goes as follows with a mild variation. So the proof is, suppose not, then let P1 less than P2 less than PR be the complete set of primes congruent to 3 mod 4. So what we now do is we construct a new number which is 3 mod 4 out of this. So that 3 mod 4 number has to have a prime 3 mod 4, because if it has, it's first of all odd, it's 3 mod 4. So all its prime factors have to be odd. But the prime factors have either to be 1 mod 4 or 3 mod 4. They cannot all be 1 mod 4 because then the product will be 1 mod 4. So that's where we exploit this thing about the special feature of 4. Okay. So now consider n. Just multiply this product by 4. So now you've constructed a number which is 0 on 4, and you subtract 1 from it. So then n is congruent with 3 mod 4. So that implies that there exists at least one prime dividing n, p congruent with 3 mod 4. But that prime p divides n, and that prime therefore must be relatively prime to this product. But p divides n implies p must be relatively prime to 4 times this. Hence p is a new prime. And so we have the theorem. So simple as Euclid's idea is, therefore the list is incomplete. It's actually quite nice in the sense that you can adapt it to other situations. So you can adapt it to this situation and prove infinitely many primes 3 mod 4, but you cannot use this to prove infinitely many primes 1 mod 4, because if you construct a number of the form 1 mod 4, it doesn't guarantee that there is always a prime number that divides that number, which is 1 mod 4, because that number could be an even product, a product of an even number of primes of the form 3 mod 4, and you can get 1 mod 4. So it doesn't fix that 1 mod 4. Okay, so similarly, you can show there are infinitely many primes 5 mod 6, because 6 is another number which has precisely 2 relatively prime residue classes, 1 and 5, and the product of the 1 mod 6 primes will be 1 mod 6, so we can use this same idea to show that there are infinitely many primes 5 mod 6. So let's just write this down. Similarly, one can show there are infinitely many primes congruent to 5 mod 6. Okay, so now let's look at just 1 mod 4. How do we show that there are infinitely many primes congruent to 1 mod 4? There are many ways to do it, but each one of them will require an idea. So one of the things I'm going to use is what are called Fermat primes. Are there still any computer science students left in this audience? One of the first questions they asked me was, is this going to be useful in computer science? I said, yes, it will be useful, but I don't know if it's useful in the sense you think it's useful. They want probably factorization algorithms or something, and then these persons disappeared. But there was one Indian guy who still continues to come from time to time. Anyway, so I'm going to use Fermat numbers to prove this. And Fermat numbers are of some interest to people in computer science. Okay, so let's just make a comment to prove that there are infinitely many primes congruent to 1 mod 4. Not that this is not an idea. Another idea is needed. Not just you. Okay, so there are several ways of doing it. So I'm going to do it using Fermat numbers. So alright, so theorem. There are infinitely many primes congruent to 1 mod 4. Proof. Consider the Fermat numbers Fn. It's 2 to the 2 to the n plus 1. Now, recall from your course in elementary number theory that 2 to the power of m minus 1 is prime if m is prime. But 2 to the power m plus 1 is prime if m is only when m is a power of 2. That doesn't prove that every 2 to the 2 to the n is prime. That's what Fermat thought. So the first few values of this will all be prime numbers. 2 plus 1, 3, 2 squared plus 1, 5, 2 to the 4 plus 1, 17, and the next one also, 2 to the 8 plus 1, 237, they're all primes. And so one of the things that Euler did was, so Fermat did not prove many things, but the French, of course, consider him to be the father of modern number theory, and they're very proud to sort of assert that. I mean, everything started with France, and they're very happy about Fermat. But Fermat did not prove many things, including the great theorem of Fermat, which became a theorem only at the end. So I remember an article, beautiful article by Andrew Graham, Fermat's last theorem, and theorem at last. Because until then it was only a conjecture, right? But the people refer to it as Fermat's last theorem. So anyway, Fermat thought that these were all primes. And I think Euler factored F5 or F6 or something like that. So Euler either disproved some of Fermat's statements or he proved many of Fermat's statements. Anyway, consider the Fermat numbers. So one interesting property about the Fermat numbers is that the Fermat numbers are relatively prime. The left one. The Fn are pairwise relatively prime. Very nice. Okay, so let's do proof of Lambda. Very easy. So consider Fm and Fn. So let's say m less than n. Since I've got Fm and Fn with m less than n, your Fn, first of all, divides Fn minus 2. So Fm is 2 to the 2 to the m plus 1, right? And Fn minus 2 is 2 to the 2 to the n minus 1. So 2 to the 2 to the n minus 1 factors into 2 to the 2 to the n minus 1 times 2 to the 2 to the n minus 1 plus 1, right? A plus b, a minus b, a squared minus b squared. And if m is less than or equal to n minus 1, this will definitely divide that. This will factor further. Or if this is equal to that, if m is equal to n minus 1. So this is true. So what does that mean? If the Fermat numbers are pairwise relatively prime, the collection of prime factors of the Fermat numbers will be an infinite number of primes. So this is another way to prove that there are infinitely many primes. Every Fermat number will generate a new prime factor. It's either prime or the prime factor it generates is different from the prime factor another Fermat number generates. Okay. So each Fermat number, i.e. each Fermat number will generate new primes as factors. Okay. Or I should say the factors of the Fermat number will generate. Okay. So it's clear what I'm saying. So now the question is, what are the factors of the Fermat number? These are numbers of the form 1 mod 4. But interestingly, their factors also will be 1 mod 4. So lemma 2. Let P divide a Fermat number. Except when n is at least 2. You immediately jump at me and say, sir, the first Fermat number is 3 and 3 is not 1 mod 4. Yes, I grant that. Okay, this is n greater than or equal to 2. N greater than or equal to 2. Then P is 1 mod 4. Why? Proof. P divides 2 to the 2 to the n plus 1. That implies 2 to the 2 to the n is congruent to minus 1 mod p. That means 2 to the 2 to the n minus 1 squared. That's why I need n greater than or equal to 2, otherwise I won't have this. 2 to the 2 to the n minus 1 whole squared is congruent to minus 1 mod p. So that means minus 1 is a quadratic residue of p. That means P 1 mod 4. Done. So the two lemmas together imply the theorem. So that's why I say you need some sort of an idea to prove the infinitely many prime 1 mod 4, and a deeper idea to prove 1 mod 8 and so on. Okay. So hence theorem. I think this is a nice proof. This is not the proof usually given in books. It's given as, I think, as an exercise in Newman and Superman. But I think it's nice enough because it sort of brings in the role for one others and so on. Okay, so what was Dirichlet's idea? How did he arrive at the proof? So this is a natural thing to conjecture, but how do you prove this? So we go back to Euler's proof of the infinitude of primes. So how did Euler deduce the infinitude of primes? So Euler's proof, as you recall very early in the course, was if you take the sum of the reciprocals of the primes, this is actually asymptotic to log of x. He was actually able to show something like this. And consequently, since this or series diverges, that floating in the form of x series diverges. And so he deduced that there are infinitely many primes. So now what we are going to prove, following the Dirichlet idea, yes, so we'll state this theorem of Dirichlet. We will show theorem 2, we want to improve that, so this is our theorem of Dirichlet. Is that the sum of the reciprocals of the primes congruent to L mod k diverges, so infinite series diverges. But he actually, we are going to show is asymptotic to 1 over phi of k log x for each L satisfying L2. So in other words, by the way, this is sometimes called Dirichlet density. This is not, we're not counting the actual number of primes up to x, but we're counting each prime with weight 1 over p. And so this is a slice of this series into phi of k subsets, so to speak, because if the residue class L has a prime factor with k which is greater than 1, then there is only one prime in that residue class at most. So if you say like 3 mod 6, well, there is a prime, 3 mod 6, 3, but then afterwards, nothing. So you have to remove, if at most, a finite number of primes from this list, and then the remaining parts of the series are now split into phi of k sub-series corresponding to these residue classes. And what Dirichlet is saying is that these phi of k sub-series are all of the same, asymptotically of the same size. So it proves more than saying there are infinitely many primes in the arithmetic progression. It sort of seems to say it is the expected number. But you will say, so that we know that there's 1 over p and so on, they are sort of weights which don't really tell the truth. What you are really interested in is the actual count of the number of primes up to x asymptotic to L. All right. So this leads one to conjecture what? The following. Let pi xkl be the number of primes up to x congruent to L mod k, where L and k are relatively prime. So now we will follow the prime number theorem for arithmetic progressions. We're going to prove that next semester. Prime number theorem for arithmetic progression says pi x k l is asymptotic to, well, what you expect, the number of primes. That's so log x. Now I got to divide by 1. In fact, we will prove this in a strong form. We can show that this is equal to that plus capital O of x e to the minus root log x for every L, relatively prime to k. And we can in fact make the k go all the way up to a power of log x. So that's called the Siegel-Waldfish theorem. So we will prove a uniform version of this called the Siegel-Waldfish theorem. So that's sort of in the back that you've got to keep in mind. So the prime numbers are, so to speak, uniformly distributed in every reduced residue class modulo k for every k. And now we want k to vary with x. So Siegel-Waldfish tells you that it's possible for k to go up to a power of the log. Okay, so that's the Siegel-Waldfish. Okay, so now let us get back to proof of Dirichlet's theorem. There are going to be a number of preliminary ideas. These preliminary ideas will be used in the proof of the Siegel-Waldfish theorem. So what I do here, I don't have to repeat, I only have to remind you when we come back next semester. So I mean preliminaries. Okay. So the preliminaries involve the definition of what are called characters. In this case, they're called Dirichlet characters, but those of you who have had abstract algebra, I think the graduate course in abstract algebra will deal with the character group. I'm not sure whether the undergraduate course deals with group characters. We normally do up to Searle theorems and stuff. But anyway, so one can either approach this from group theory by defining and studying group characters first, and then specializing that to the proof of multiplicative residues mod k. But I'll just do straight away for Dirichlet characters. Okay. So we're going to define Dirichlet characters. So what is a Dirichlet character? Here's the definition. A Dirichlet character is a function chi. It's an arithmetical function. So it goes from the integers to the complex numbers. That's any arithmetical function, which satisfies the following: several conditions. Well, you might think, how can something satisfy so many conditions? Well, we just have to assume, we'll deduce that it does. We can construct functions that satisfy these conditions because the group of reduced residues, the set of reduced residues is a group. So we get it from there. So one condition is chi of mn is chi of n for all mn. So this is completely multiplicative. So that's one of the properties of a character. It's not just multiplicative in the ordinary sense, it's completely multiplicative. And I'll give you an example of Dirichlet character. The second condition is that the character is 0 if and only if n and k are relatively prime. So I should really say a Dirichlet character with respect to k, modulo k. There is a modulus lurking in the background. So this is a character with respect to k. So this is 0 if and only if n and k are relatively prime. So it doesn't look at numbers which are not relatively prime. It focuses on numbers which are relatively prime. So that's a multiplicative group. And then the third.
Do you want not equal?
That's what I said, but I wrote something else. Okay. Now the third property is that chi of n plus k equal to chi of n, right, for all integers n. So this is periodic with period k. Okay. Now, these properties, first of all, tell you that the chi is really now property 3 tells you that chi is a mapping from the residue classes mod k to the integers. So from 3 we see that chi can be considered as a mapping from the residue classes, all residue classes, modulo k to the integers, but the support of chi is in the reduced residue classes mod k. But the support of chi is z k cross the reduced residues mod k. Now there is one very simple property. Okay, so one thing is clear from this, that since the reduced residues form a group, okay, well first of all, something here, okay, clearly, chi of 1 is 1. Because chi of 1 is chi of 1 times 1, which is chi of 1 times chi of 1 by the multiplicative property, and chi of 1 is non-zero. So those two imply that chi of 1 is 1. Now, your zk cross is a group, a multiplicative group. Order phi of k, the Euler function. Now every element of a finite group has an order, and the order divides the order of the group. Okay, that's your a to the power of phi of n is 1 mod n. That's Euler's theorem. So from this it follows that for each character k, chi of a to the power of phi of k is equal to 1 for each which means it's a root of unity, a phi kth root of unity. So in particular, chi of a is the root of unity. This is important. We're going to use this very soon. So in particular, chi of a has absolute value 1. Or 0. So what does this mean? This means that the Dirichlet series, summation chi of n over n to the s, converges in the half plane s greater than, real part s greater than 0. Thus, Ls of chi defined to be equal to summation chi of n over n to the s is absolutely convergent in sigma greater than 1. But the chi is totally multiplicative. Therefore, Ls of chi now have an Euler product representation. Right, because chi is completely multiplicative. But if the Euler product is convergent, that means Ls of chi is never 0 for each chi in sigma greater than 1. Ls of chi from 0 for each chi in sigma greater than 1. So like the Riemann-Zeta function, this is non-zero in that. So the modulus changes, and for each modulus, there are different characters. So, but now you will say after all this, so I'll give you one good example of a character. Well, First, the trivial character. Chi-Fs is 1, but all the residue classes, on every reduced residue class, it's 0 otherwise. That's called the principal character. So we'll use that. Principal character. So we'll call the character Chi1. Alright, is equals 1 if for every a relatively prime to a. 0 if, of course, this we know. So this is just 1. So this will then be a Riemann-Zimmer function, except for a finite part. So in this case, Ls of chi is the Riemann-Zimmer function multiplied by the product 1 minus P s e divides k. Just that part has to come up because the primes that divide k are those that contribute to the numbers having a prime factor, common factor greater than 1. Right? Therefore, that's the factor that comes up. Right? Now, you'll say, sir, even this is trivial. So let's give an example of a non-trivial character. One good example of a non-trivial character is the Legendre symbol. Okay, so Legendre symbol is an example of Legendre symbol mod 4, let's say, is an example of a non-trivial character. Because it's periodic, and you can later go to Jacobi symbol if you have come out of those. But Legendre symbol 1, 4 is an example of a non-trivial character. Okay, now why is it we need characters to study this? Well, there is a trick which you must have used, regardless of whether you did analytic number theory or not, and that is you use roots of unity to select specific numbers in a residue class. Because the property of the roots of unity is, if you take any root of unity other than 1, the sum of the powers of that root, if you take the sum, but let's say it's the nth root of unity, you take that number zeta squared, zeta to the m, that sum will always be 0. So what we do is we judiciously use the roots of unity to select integers in specific residue classes modulo k, modulo n. But here we are looking at reduced residues. So we have roots of unity, but we need, see, the ordinary residue classes modulo m are a group under addition. So if you take roots of unity, e to the 2 pi I j over m, e to the 2 pi I j over m times e to the 2 pi I j prime over m is e to the 2 pi I j